So our next session, I'm sorry. Science and industrial innovation with quantum accelerated high-performance computers with Dr. Peter Eder, Head of Partnerships at IQM. Peter, you're already there. The stage is yours.
Hi. Thank you so much for the kind introduction. As said, my name is Peter from IQM Quantum Computers, and today it is my pleasure to talk to you about science and industrial innovation with quantum accelerated high-performance computers. Sorry, it's not working on my laptop. I want to start by citing Thierry Breton, the European Commissioner for the Internal Market. He said by 2025, Europe will have its first computer with quantum acceleration, paving the way for Europe to be at the cutting edge of the quantum capabilities by 2030. So this really nicely reflects the title of this talk, so Science and Industrial Innovation. Quantum computers clearly come from science. Quantum mechanics, most of us think of this like magic, and now we want to make it an industrial innovation. So let's see, what is the main application areas where you can use quantum computing? Well, obviously, I was talking about science, but I'm not talking of the science behind quantum computing. I'm talking of what can we use it for. So let's have a look. We can use it to attack biology problems. We can use it to attack chemistry problems, obviously physics problems, math problems. Well, okay, we are using computing to do so, and we all want to use it to do machine learning. So what's the huge advantage of this? I think most of you know, but anyhow, let me repeat it for you. We do have intractable problems that are out there. So there's a class of commercial problems that can never be solved with classical computers. I'm seeing a lot of computer scientists here, so that should be the NP-hard problems. There are fundamental limits. There are not enough atoms in the universe to build a large enough memory and computing. The answer would take thousands of years to attack these above problems. The very nice example is coffee. We do have about 13 atoms in this molecule. If we want to simulate it, we run out of computing power nowadays. And very important topic is sustainability. So actual data centers use a huge amount of power, while with quantum computers, we are talking about energy consumption of some kilowatts, or power, sorry. So what do we think how this will evolve in the future? We see three phases. Right now, we see ourselves being in a foundation phase. Industry is exploring the potential of this new technology of quantum computing. Then there will be an advantage phase. This is what Thierry Breton was talking about. So when we see the first use cases where we explore quantum advantage. And then, that's what we expect to happen, this will truly disrupt industry fields. I, myself, would like to compare this to the internet. So we will have this huge amount of computing power available, and the things we can do, I today can't imagine, but we, in the last talk, heard a lot of nice things we can already do with the computing powers we do have today. The talk is named Science and Industrial Innovation with Quantum Accelerated High-Performance Computing. We were doing a survey with HPC centers, and of these 110 HPC centers in these surveys, 76% want to adopt quantum technologies by 2023. Well, one way or the other, that has to be said. Not all of them will have a quantum computer on-premise right now. But 71 of them want to adopt it on-premise by 2026. That's a very, very interesting fact. And this actually brings me to tell you, okay, well, how does a quantum computer look like? How can we build such a thing? Well, obviously, at the very bottom, you have this quantum layer. This is where, for example, I was working back then as a PhD student. That's for the physicists. On top of this, you do have a control layer. You do have control and measurement layer. You have a control processor layer. Then we are there we are using more classical computers to really control the quantum bits. And at the top level, you do have the host level. That would be the HPC computers or HPC center interacting with the quantum computer, giving this huge computing power. If you want to learn more about this, visit us at our booth at the marketplace. And I've seen the colleagues from IBM, IQM, do have a really cool VR demo downstairs in the main hall. So how do we think business can be made from this? Our belief is we have to go full stack. So really from producing the chips, or designing them, producing them, integrating them to the aforementioned HPC centers, and then innovate on this for particular applications. I will come to that later on. Okay, then I wanted to show you two things we are proud of. We did a very nice co-development project in Finland with VTT, and we were able to close a deal with German government in Germany. Oh, well, yes. Okay, I was talking about innovating on use cases and particular applications. How do we think this is possible? We think this is possible by doing hardware-software co-design. So we take a use case, we take an algorithm, and we take the hardware at hand, and we adopt all these pieces to work together as perfect as possible. We recently did a scientific publication on this, where we were exploring a problem in NMR imaging, where it turned out the problem at hand, the use case, has a star-shaped topology. So our engineers asked themselves, okay, why not build hardware using a star-shaped topology? And it turned out they were able to save 90% of the gates needed to do this algorithm. That's very important in the current so-called NISQ era. That's the near and intermediate scale quantum era, which simply means hardware is not perfect enough. Okay, so I was talking what is a technical differentiator, co-design, we love it. But the other thing we love, and which is the real superpower, is our team. And I heard on the main stage Christina Raab from Accenture talking about this, that none of us really realizes how important it is to have the correct talent in your team. More on talent, we are hiring as well.